All right. We've already seen how we can use probability generating functions to derive the distribution, or at least the generating function of a sum of independent random variables. And now we're going to show how this can be used to actually pretty easily derive the distribution of a sum or properties of a random number, a sum of a random number of independent random variables. So let's see how that works. So the idea here is that we actually have two random variables, well, two families of random variables. We have a count random variable n, which means n takes values in the non-negative integers. And we're going to let x1, x2, etc. be an IID sequence of random variables such that n, x1, x2, etc. are all independent of each other. Okay. Then what can we say? What can we say about the distribution of we'll write S sub capital N, which is defined as the sum from x1 up to x sub capital N. So we have a sum of random variables, but how many of them we add up? So we have indefinitely many random variables, x1, x2, x3, etc. How many of them we actually add up is a random number itself. Okay, and this has a probability generating function. Well, let's say IID, x's are IID with a probability generating function. With PGF G sub x such that all the random variables are independent, then this random sum has a probability generating function, which we write G sub n, which is equal to the generating function of n composed with the generating function of x1. Okay. All right. Now, what's interesting about this, first of all, let me, before I prove this, let's think about this. In the case where n is equal to n with probability 1. So this is just the case where, well, let me not use too much shorthand, but with probability 1, well, let's say, in the case where probability that n is equal to a specific value is 1, then this is the same as just considering what is the probability generating function for this sum x1 up through xn, which we have shown is gx to the power n. So we've seen this in the case of the binomial. We've seen this in the case of the negative binomial. Okay. But note that the generating function of a constant, in this case, n is a constant. It's just the number, it's little n with probability 1. We showed this, we showed this up above and we could derive it again. It's just z to the power of the constant, right? So this is z to the power n. So this means we can actually write gx1 of z to the power n is actually the same. It's g of n composed with the generating function of the sequence z was x1. So that's consistent with our theorem, but here we have a more general theorem, more general relationship where we allow n to actually be a where we allow n to be an arbitrary count random variable. So how do we do this? Well, once again, the way that we're going to do this is by somehow leveraging the fact, first of all, we're going to have to leverage the fact that these random variables are independent. And we're going to leverage the fact that, well, we're going to condition. So when we condition things, why do we condition? We condition because we use the law of total probability. We condition because that fixes a random variable. Once we condition on this thing happening, we can treat that thing as if it was fixed. And that oftentimes simplifies things. And if we're conditioning on something that's independent of everything else, then once we fix it, then we can drop it out of the condition. And you know, if we're careful enough. So we'll see how that works here. So this is the definition. Let's condition on the value of n. So it could be anything. So in this case, law of total probability. So conditional expectation so we can bring a condition into an expectation. And let me explain what that means in a second. So the conditional expectation, just as an aside, right? The conditional expectation given an event, so conditional expectation of, let's say, a random variable y, given some event a. So let's let a be an event. This is just the usual sum over all possible values of y, the random variable, of y times the probability, but now instead of being but now it's the conditional probabilities. So that's the definition of conditional expectation. So as we've seen before, the conditional probability, this is a probability distribution. So it is in fact a valid probability mass function. So it's like when we condition on the event A, the variable y is effectively a totally different random variable because it behaves differently, and the behavior is captured by the conditional probability. So that's all that this conditional expectation is down here. Okay. So we have law of total probability. We go over all the events and we have conditional expectation. And now what we realize is, okay, once we have the condition that n is equal to little n, we can now watch this here. Replace the big N in the exponent with the little n. We still have the condition. Still a conditional expectation. Okay, fine. But now what? Well, notice that the random variables over here are independent of the random variable over here, right? We've assumed that the x's are independent of n. So what does that allow us to do? That allows us to drop the condition, right? When a conditional probability, when a random variable is independent of another, the conditional probability of the random variable on the other is no longer conditional. We can drop the condition. And so now the benefit of this is we don't have any random variables in the index set. We don't have any condition. And we now just have over here the probability generating function of NIID random variables, which we know how to deal with. Right, so this is just now the generating function of x1 up through xn, which we've dealt with before, which we know is the generating function of any one of them raised to the power n. Okay. Okay, but now what's interesting is, what does this look like? Well, let's see, have we written down? No, no, no. So what does this look like? Well, what is the generating function of n? Let me write it with an argument x. Okay. Well, this is just the definition. I'm not doing anything fancy here. It's n to 0 infinity, x to the n, probability that n is equal to n. Okay. So now if I substitute x in as, it looks like a complicated thing to do. But if I set x equal to the generating function of x1 at z, what do I get? I get exactly, plug in this for x, so that gets raised to the power n, and I have my probability. So this is exactly the generating function of n, where the argument x is the generating function of x1 evaluated at z, which is exactly what we needed to show. Okay. So that's nice, and that can sometimes allow us to get some nice properties of these random variables. And let's follow this up with a couple of corollaries. So using this, let's suppose that using this this theorem that we've just proven, what is the expectation of the sum of a random number of random variables? Well, we can easily show using this that it's the product of the expectation of n with the expectation of x1. How do we prove it? Well, remember we have the generating function here. And what did we show up above was that the first derivative, we can get the factorial moments by taking the nth derivative and evaluating the generating function at 1. Okay. So let's take the first derivative of this. And how are we going to do that? That's going to be the chain rule. So the first derivative chain rule, right, is ddz gn composed with g1. How does that work? It's the derivative of gn evaluated at its argument, but then we have to multiply by the derivative of the argument. Okay. Okay, let's evaluate this at 1. Gn prime gx1 of 1 times g1 prime of 1. Okay. Well, what's gx1 evaluated at 1? Well, we've also shown up here before, and we could always rederive it if we needed or if we forgot, that the generating function, probability generating function, evaluated at 1 is always just 1. Because it's just the sum of the probabilities. Okay. So gn prime is 1 times gx1 prime of 1. But what are these? Well, these are the expectations, right? The probability generating function derivatives evaluated at 1 are factorial moments. The first derivative evaluated at 1 is just the first moment. So it's gn prime of 1 is expectation of n, g prime of x1 of 1 is expectation of x1. Okay, and now what about the variance? Well, we can use a similar technique, and I'm going to leave this as an exercise. Using a similar technique to get the variance of Sn. And it has two components. It's the expectation of n times the variance plus the variance of n times the second moment of x squared. Or no, times the expectation of x squared. Okay. So I will leave that as an exercise to make sure that we're fully comfortable with how we work with generating functions to figure this out.